again, it is very, very good afternoon to all of you. And the topic that I'm actually going to cover is developing India into a global hub of the semiconductor industry supply chain. Mr. Vishal, yeah. And the agenda that I wanted to actually cover was I wanted to give a glance of semiconductor industry, right? So, over the last 50 years, I mean, how semiconductor industry has actually transformed itself globally, and it is always good to actually take a look at it. What has transpired over the last, say, 55 years. And then I would actually talk about uh, global semiconductor market size. And in that context, I'm going to actually cover Indian semiconductor story and what we've been actually doing and what we really want to do from now on to really become a global hub for the semiconductor industry supply chain. And in that context, I'm going to cover semiconductor ecosystem. So because it is important for us to understand how the ecosystem actually looks like and where we are good at, where we are strong, and where we have presence today, and the missing pieces that we are actually trying to bridge. And of course, the government initiatives that are actually having a positive impact in making India into a global hub for the semiconductor supply chain. That is something that I'm actually going to touch upon. And what we can look forward to, right? Future of this industry in India is something that I'm going to cover. And of course, MosChip, the company that I'm leading, it's been in the industry for 25 years. And we are actually celebrating our 25th year of inception. And it is important for all of you to understand what kind of contribution this company, which actually started as a fabless semiconductor company like 25 years ago, has done in India. And also because this is a project manager's global summit, I thought I would also talk about project manager's role, right, in semiconductor industry, and then conclude. Mr. Vishal? Yeah. And of course, when people talk about semiconductor, and the talk doesn't actually start without the Moore's law. Even Dr. Raghunath sir was also talking about Moore's law when he was talking about the exponential growth. Right, in 1965, I wasn't born. Gordon Moore, right, who later became Intel co-founder, he predicted that in ICs, the integration would actually double every 18 months, integration rate. What that actually means is the number of transistors that are going to be included in integrated ICs are going to double every 18 months. This is exponential again, right? And it is just what you call a coincidence that I'm talking about this exponential growth in semiconductors or exponential growth in size of the chips right after the exponential growth that Dr. Raghunath sir was talking about. And what this actually means is in about 3 years, right, you would actually quadruple, right? If you had about, say, 1,000 transistors like 3 years ago, you would have like 4,000 transistors now. And if you look at that, if you extrapolate that what I call law, you would figure out that the ICs would actually become thousand-fold denser in about 15 years. What that actually means is, if you started with X number of transistors in 1 year, in 15 years, you would actually have 1,000 times more number of transistors. And this is actually possible. This law held true for what I call for the entire semiconductor life so far. Today, people actually talk about there is end to this law, is more or less still valid and all that. But for majority of the life so far, this law actually held true. And in the diagram that I have actually shown here, the number of transistors we were able to accommodate in integrated circuits were actually increasing because the transistor sizes were exponentially what I call diminishing, right? So, and that is what we can actually understand from this slide. Mr. Vishal, yeah, we can move to the next slide. Can I get control? Would you be able to give me control?
No, sir, we are okay. We are okay.
Yeah, no problem.
Because
yeah.
it may be difficult actually.
Yeah, sure. Thank you.
You can let us.
Yeah. And again, in the last 50 years, we have come a long way. I just wanted to take two snapshots, right? In 1971, when Intel released their 4004, right? This is a 4-bit microprocessor. This had about 2,300 or 2,400 transistors. And this was actually built, designed in PMOS technology, and it was 10 micron technology. And the processor was running at less than 1 megahertz. I believe it was running at 740 kilohertz or 750 kilohertz. And 50 years, right? Fast forward, if you look at AMD MI300X that was released in 2023, this, I would actually say, what you call chip, this SoC has about 153 billion transistors. And this was actually built in TSMC 5 nanometer, and some of the other dies were actually built in 6 nanometer. This particular chip has 12 dies within the same package. It is not a single package. These are all what I call logic dies and memory dies were integrated into a single chip to give you this kind of what you call capacity in terms of what you call performance. And of course, the power consumption is obviously going to actually go up. But if you look at the kind of performance that it actually gives, this is basically targeted for HPC and AI workload applications. And you would also see HBM3, what you call memory stacks are used on this chip. And it is just not the logic technology that has actually advanced. And it is also the memory technology that basically grew leaps and bounds. Today, you would find high bandwidth memory, HBM3E, which can actually support 9.2 gigabits per second per bit. And it has about 1024 lines, and one HBM3E memory could give you 1.15 terabytes per second, what I call kind of bandwidth. And if you have to understand the importance of 1.15 terabytes per second, the way you can actually understand that is, say, if you take a full HD movie, and a full HD movie might occupy 5 gigabytes. So if you have a full HD movie of 5 gigabytes, 230 such HD movies, you could actually process it using that kind of bandwidth in 1 second, right? That is the kind of what you call memory bandwidth that we are talking about. We have truly come a long way in the last 50 years. Yeah, please move on to the next slide. And this is another slide that I basically took from Tokyo Electron Limited. And this gives basically timelines about the core technology, have, triodes, diodes, BJTs, MOSFETs, CMOS technology, and the nanotechnology that we are in today, and the applied technologies, right? And we started with radios, then TV broadcasting, then computers, personal computers, laptops, and of course, the smart mobile phones, then smart mobile phones, and networking, telecommunication. If you look at any walk of our life, and semiconductors are actually used. And I'm sitting in home and doing this presentation, and you could actually imagine the semiconductor, what you call a role in this whole communication. Our homes are becoming smarter, our offices are becoming smart, and our vehicles are actually becoming smarter, and so on and so forth. So in every walk of our life, both the personal and professional, semiconductors are playing an extremely important role. And with the what do you call advent of say AI, this industry is going to exponentially grow. That is something that I'm going to show you in the next slide, Mr. Vishal. Yeah, I mean, again, this slide actually talks about the timeline summary. In the 1990s, we basically had processors that were being built in 180 nanometer and 90 nanometer technology, and the number of transistors were about 40-50 million transistors, and we used to have BGA kind of packaging. In 2000s, and we basically had multi-core processors, and these were actually being built in 45 nanometer process nodes, and flip chip packages were basically what you call being deployed. And in 2010s, the FinFET technology took over, and the capacity, I mean, the need for the capacity increase has actually come. GPUs and TPUs to basically process large amounts of data, large scale processing, high performance computing has come into play. And with that kind of what you call SOCs, 2.5D integration, 3D integration, system in packaging has come into play. In 2020s, right, the decade that we are in today, we have SOCs that basically have chiplets. The MI300X that I actually shown you, that is an SOC that basically had about 12 dies. So chiplet is one die, and within an SOC there are going to be multiple chiplets. And we are seeing a lot of SOCs that are actually being built with many chiplets with logic, memory, and IO dies that are giving more than 100 billion transistors with a very, very complex architecture. And these are being used for the high performance computing and AI workloads, right? Yeah, let's move on to the next slide. And this gives a glimpse of the packaging technology advancements. Of course, I mean, we started with a dual inline package. That is what you had actually seen with the Intel 4004. Today, we have 2.5D and 3D integration. You basically have uh, multiple dies that are sitting on a silicon interposer. Those are horizontally connected. That's called 2.5D integration. And 3D integration is you basically have die sitting on another die, and these dies are going to actually talk to each other through silicon via kind of structures. And this 3D integration is basically both horizontal and vertical integration of the dies. The way we basically have these apartments actually built, a similar thing is being done even in what I call chip industry. And the packaging technology does come a long way, and you can actually see that from this slide, Mr. Vishal. And of course, I mean, again, as I said, because semiconductors play a very, very important role in every walk of our life, and also with the AI explosion, what has actually happened is this industry, it actually grew from, say, for example, nothing to about $500 billion by 2020, and it took 50 years for the industry to become a $500 billion market. But from 2020 to 2030, in about 10 years, it is going to reach to $1 trillion almost. So what that means is the growth we had actually seen in 50 years is going to be seen in about 10 years. And it is mostly thanks to the high performance computing and applications that the industry is what you call trying to chase and solve. So this is a huge exponential growth. And because the market is going to exponentially grow, it is important for us, I mean, India, to actually pause and take a look at it and see how much of it we are going to actually capture. That is something that that is being looked at, right, by the industry and by the government of India. And that is the story that I mean, I will talk about over the next few slides. And Indians, yeah, excuse me. Can you go to the previous slide?
Yeah.
Thank you. So Indian semiconductor history and transformation, if you look at it, and in what do you call at the start, most of us, I mean, most of the semiconductor life, what do you call in India was in R&D, and we were actually helping foreign country-based multinational companies, and we were actually involved in design both front end and back end, and we were helping MNCs to build their what do you call SOCs. And there were companies like, I mean, TI, AMD, Intel, Broadcom, Qualcomm, and all those companies had captive center. I mean, they basically started captive centers here, and we started helping them on R&D. And down the line, I mean, with that experience, with that support, we actually built excellent expertise in R&D, right? Chip design is something that became, I mean, a very, very reliable skilled resource in India. And today, 20% of the world's semiconductor professionals actually work out of India, right? And what we were mostly focusing on the design, but if you really want to become a global hub for the entire chain, it is just not the design. I mean, we will also have to have fabs, and we also need to have packaging and testing houses, ATMP and OSATs. And that is something that we actually started. I mean, even though we had SCL that actually started in what do you call 1980s, but a full-blown commercial fab is something that we actually started looking at through the government of India's initiatives in early 2020s. Yeah, can you move to the next slide, Vishal?
Yeah.
And Indian semiconductor market size, again, I mean, global semiconductor industry, I mean, that market size is going to be around $1 trillion by 2030. And our semiconductor market size is expected to grow to $100 billion by 2030. When I say semiconductor, I'm actually talking about the components and the ICs. I'm not actually including the end product, right? The electronics would probably grow to 400 or $410 billion. But this is purely the semiconductor market size. And the majority of it, as you wouldn't be surprised, is actually going to come through handsets, right? I mean, today, I mean, India is probably the second largest mobile manufacturing country, right? And a lot of semiconductors that are actually required in what you call handsets that are going to be manufactured are going to be sourced out of India. And then the IT, telecom, industrial, consumer electronics, automotive, aerospace, defense, and wearable. I mean, these are all the industry segments that are actually going to have a substantial growth over the next 5-6 years. And the market size is predicted to grow to $103 billion. Yeah. Move on to the next slide. And a typical chip design cycle actually looks something like this. And the activities that are actually shown in the dotted box are the ones that I was talking about, right? We are actually good at it, right? And we are good in front end and back end design, and chip design is something that we have a lot of expertise. And the boxes that are actually shown in shown in the bottom, right? Fabrication, OSAT, and ATMP. These are the what I call missing pieces, and these are the ones that are actually being what I call initiated right now, so that the entire semiconductor supply chain is going to be completed, right, Vishal? And semiconductor ecosystem looks something like this. I mean, you basically have fabless design companies, and you also have fab, and of course there are going to be IP providers and design services companies, and then then for within the fab, you would actually have manufacturing equipment, right? Then photomasks shops need to be there, and apart from this, you obviously need to have silicon suppliers, and fabs need pure water and uninterrupted electric supply. And of course, we also need the talent, and hence universities and training centers will also play an important role in creating talent, right? Who can actually work in design, in the fab, and even in OSAT and ATMP, what do you call, plants. And of course, public-private partnerships, and then government support, right? Apart from this, there are, going to be product engineering, companies that are going to support us on the test development, reliability testing, quality testing, lab bring up, and in chip design, the other most important player is the EDA companies, right? The design automation tools, and these are the tools that are actually used in chip design cycle, right? So this is how a semiconductor ecosystem actually looks like. Yeah, Vishal. And we talked about the importance of the government initiatives. And as we all know, under production linked incentive, right, PLI, government of India had allocated about $10 billion, and which has actually started attracting, global players to start collaborating with Indian players to start fab and OSAT and ATMP, right? Micron is actually investing in an OSAT in Gujarat. They are making $825 million in an estimated $2.75 billion plant. 70% of it is actually coming from central government and the state government. And this is basically a huge what do you call, development over the last 18 months or so. And AMD is also planning to invest about $400 million over the next few years to increase their capacity and capability in R&D, and they are actually planning to increase the number of engineers to about 10,000 engineers in the next few years, and that would actually become their largest design center on the planet, right? And as I said, universities and training centers also play an important role in creating talent. And what I understand is, under what I call CDAC guidance, and through Chip-in initiative, a lot of universities, I believe there are more than 100 universities that are given access to EDA grid, EDA tools, so that the engineers could actually do, design, say, small circuits or small, what I call, microcontrollers, simulate and get some hands-on experience. And these engineers, if they are actually trained that way, they would become, project ready or industry ready, when they come out of colleges. And then there is an investment in infrastructure. Special economy zones are actually created, and again, for some of these fabs and OSAT, clean rooms need to be there. Again, as I said, uninterrupted power supply needs to be there. Water, pure water supply needs to be there. That infrastructure is actually being built, right, Vishal? And so there are about 45 applications that government received as of October 2023. And this is as per IESA report. IESA is India Electronics and Semiconductor Association. There are about 5 applications for semiconductor fabs, and one is actually approved, 2 for display fabs, and 9 for compound and OSAT ATMP plants. There are, a couple of OSAT ATMP plants that are actually approved. One is coming in Assam, the other one is coming in Gujarat. There are about 29 applications that government of India has actually received under design linked incentive, and there are about 13-14 applications that are already approved after what you call due diligence. And I would like to proudly say that MosChip has also participated in under DLI scheme, and as we are planning to work on a smart energy meter IC development under DLI, right? So nation's upcoming fab and OSATs. I mean, again, as I said, of course, Tata Electronics with PSMC is building India's first AI-enabled fab at Dholera, Gujarat, and the expectation is that first chip is going to come out in 2026, and this fab is expected to manufacture about 50,000 wafers a month, and we have access to technology nodes like 28, 40, 55, 90 nodes. And I talked about two OSAT facilities. One is in Assam, the other one is going to be in Sana and Gujarat. And the Assam OSAT facility is expected to what do you call deliver about 48 million units per day, and the Gujarat one is going to deliver about 50 millions per day, right? And these are the expectations. Yeah, Vishal. Yeah, see, I mean, after building so much of good expertise in design, and we've also actually started investing in fab and OSAT. Design, fab, packaging and testing would actually say complete the entire supply chain. But again, I mean, for fabs, apart from the water and electricity, you also need to have chemicals and gases, right? Indian chemicals and gases, I mean, can actually support majority of the chemicals, gases, and minerals that these fabs need, but they may not be semiconductor grade. I mean, they need to be actually pure, and hence some investment will have to actually go in there to basically make these semiconductor grade chemicals and gases that could be used in fabs. And I'm aware of the fact that SCL has done some work on this, and they made about 35 minerals that are what I call good for semiconductor manufacturing. And the government initiatives will definitely bring in the cutting edge semiconductor technology, and it will also create a network of semiconductor design companies. Again, as I said, there are about 14 applications that are approved under DLI. They are building indigenous ICs that are going to be sold hopefully in millions, both domestically and internationally. And a lot of these chips are expected to be manufactured in Indian fab, and they are going to be packaged at the OSAT centers that we are trying to build, and then use them domestically and internationally. Today, I mean, if you look at it, our semiconductor requirement, right? It is only 8% of the country's total semiconductor consumption or semiconductor requirement is fulfilled locally. What that actually means is 92% of the semiconductor needs or the components or ICs are being imported right now. And it is expected to grow to 20% by 2030. And again, I mean, even though it doesn't actually look really big, but this is going to happen in 6 years from now. But I mean, when we basically have that kind of a growth, and the time is not too far from 2030, hopefully by 2047, we would truly become a self-reliant, what I call, nation as far as semiconductors are concerned. That is what we can absolutely look forward to. And again, MosChip's contribution over the last 25 years. I mean, very recently, again, as I said, we are approved under DLI to develop a smart energy meter IC for both the domestic and international markets. That is something that we are actually working on. And we have also won design, development, and delivery of India's first HPC processor SoC. And this is named OHM. This is going to be built in TSMC 5 nanometer. We have partnered with a Japan headquartered company, Socionext, to build this. And we are very, very excited to have gotten this opportunity and to build this first ever HPC processor for what you call India. And we also have a training institute. It's called MosChip Institute of Silicon Systems. And over the last 13 years or so, we trained more than 2,000 semiconductor professionals, 30% of which we consumed, and 70% of which went to they were able to get a job in other companies. So that is the kind of contribution we as a company actually did to the ecosystem. And over the last few years, working with a lot of tier 1 semicon companies spread across world, we taped out and built 200 plus ASICs for these companies. And MosChip, it is not only known for its semiconductor expertise, we also have presence in embedded software and system design. There are about 500 plus systems that we actually built for customers worldwide. And in our initial phase, for the first few years, MosChip built some connectivity ICs that we actually sold in millions. So this is the contribution that MosChip had over the last 25 years in India. And a lot of you may not actually know, this was the first fabless semicon company that was founded in India, and we are a public limited company. And also, without the project manager's role discussion in semiconductor industry, we cannot actually end this session, because this is a project manager's global summit. And project manager's role is extremely important, because some of the HPC chips or AI chips that are being built these days, you will have to spend a few tens of millions of dollars. In some cases, you will have to spend more than $100 million to basically develop a chip. And the project management becomes an extremely important step. And the project managers are going to play an important role, collaborating internally and collaborating with teams externally, because the external teams are going to be the IP providers, the EDA tool vendors, of course, the customers, the foundries, OSAT partners, and so on and so forth. And the communication, tracking, quality checks are going to be extremely important in project management, in IC design and development. And it is also important to deliver or bring chip on time. Otherwise, you would also lose out to your competition. And hence, timely project completion, first pass silicon success is the most important thing that we need to achieve in this industry to stay alive and to stay relevant. And with that, I would conclude my session. Thank you so much.
Thank you, sir. Very comprehensive session. You started with the inception of the semiconductor industry and how it's grown over the years, and have explained very comprehensively the semiconductor ecosystem. Also very powerful numbers in terms of the India semiconductor mission and how the local consumption is expected to increase by 2.5 times within the next 6 years, and what it means in terms of capacity building, and also in terms of creating manpower and resources, and what how project managers are important and where they fit in terms of the the value chain of the entire semiconductor industry. So very comprehensive, sir, and excellent presentation.
Thank you so much, Vishal. Thanks for the opportunity. Thank you so much, Dr. Pillai, sir. and I'm really grateful for the opportunity. Thank you.
Thank you, sir. Thank you.